Hello, my name is Martin Holst Swende, and I am the security lead for the Ethereum Foundation. Today I'm going to talk a bit about EVM forensics and managing attacks against the network and how we've been working on that. So I've been security lead for 1 year. I started just before DevCon 2 in Shanghai last year, which started off with the Shanghai attacks roughly 1 day after I started my new role. It kept on for a month. We've also seen during the last year we have done 3 hard forks. We've had 1 unintentional consensus split. There was a DOS attack against specifically the Geth client. There has been thousands of Ether stolen in more and less sophisticated attacks, both on-chain and off-chain. We had the testnet totally brought to its knees and then resurrected again. And of course there's the standard IT incidents with leaked databases and someone taking over someone's phone number and their account and attacking our GitHub and stuff like that. So we should all be very clear about where we're at. This is crypto land and we're all in crypto land. And it's like Australia, where anything with a heartbeat will try to kill you. And if you make a mistake, you're probably dead. So, meanwhile, for attackers, they have never had it better. They no longer need to hack point of sales computers and trade carding details over shady forums. They can just hack a computer or somehow get some cryptocurrency and immediately turn it into value. And it's like a Wild West in Australia right now. These are the Shanghai attacks. I'm not going to talk that much about them. The first Shanghai attack is that little blip down there. And then it just kept on going for a month. And it was a lot of different attacks, mostly targeted towards Geth. But when the dust is settled after incidents happen, then that's when you can actually do something about them and think about how can we be better prepared next time something similar happens. And how can we prevent it? So how can we improve the readiness and the resiliency? So for readiness, it's about detecting attacks and performing analysis quickly. So we started improving that with some monitoring, adding up some monitoring nodes that we run in the cloud and adding some graphs. Turns out there were some inherent issues which hadn't been noticed before, with transaction propagation inefficiencies, which over the course of a few months in the beginning of, from January 3 to March, we managed to bring down the overall network traffic with about an order of magnitude just by removing invalid transaction propagation from the clients. On these monitoring nodes, we also added some interface so that we can extract very detailed information about what are the canonical blocks in the chain. And if we see a consensus split, we can get very detailed information about the receipts and differences in these and quickly point out which transaction caused this consensus issue. So here you see is a Geth master and Geth develop and the parity node. And right in this image, they're differing on 2 fields marked in red there, and that's because parity RPC interface exposes a few different fields than Geth. Now, as we go into analysis, I'm going to talk a few words about the EVM, because there might be a conception that any minor difference in the implementation of the EVM will automatically result in a consensus failure. And that's not quite true, because there are some things, some parts of the EVM which are ephemeral, such as the memory and the stack, and which do not necessarily trigger consensus issues. But they're very interesting because they can be used to trigger consensus errors. And in order to really measure EVMs side by side and detect implementation differences in EVMs, we need a kind of op-by-op view of the internal state. So we push kind of hard to get a common output format for EVMs, so that after each instruction made in an EVM, it would output a JSON blob with the internal state, as you can see on the left. And also a capability to use arbitrary pre-state and genesis configuration with the raw EVMs. So one problem that can arise is if we're hit by an attack which blows the node out of the water. How can we analyze that? Because our node just died, right? How can I analyze a transaction if the transaction crashes my node? Well, if we have a standalone EVM, what we can do is we can just fetch the pre-state about the sender and the receiver, just those two accounts. And we can execute that locally in our EVM and then analyze the trace to find, did we miss anything? Was there anything else we should have had here? And external references, and fetch those and start over. And if the node crashes, then we've successfully reproduced the API, the transaction. And for this, we only need a Web3 standard API without any debug specialities. Sorry. So I'm going to demonstrate quickly how we can do analysis of the jump test attack, which we were hit by on June 1. So I'm running this little reproducer here. I pipe in the hash used in the attack, the transaction, telling it I want to use my local EVM, not through Docker. And it basically sets the right fork rules for that particular block and executes it. And it has some intermediary traces here. We can take a look at those. So well, let's go directly instead for the final trace. I'm showing this in what I call the op viewer, or retro mix if you like. It's a remix like debug viewer for the JSON output format that I showed earlier. And this is a good start for analyzing what's happening in a transaction. So you can see this particular transaction, it does an Xcode copy. And the Xcode copy fills the memory with 5B. And it does it repeatedly. And as you can see, the memory is growing. And it keeps doing this for about 600 steps. I'm going to go a bit faster here. Until it has filled up the memory with 0.5 megabytes, all 5B, which happens to be jump test. Then it puts some more code in there. And this looks like actual EVM code, 6003565B. And all of you, I'm sure, recognize that that is the push one, jump test, and stop. So it just executed a create with that code. And as you can see, the size of the create is the full 0.5 megabytes. Okay, so now we know that the attacker is doing creates, and he keeps doing it repeatedly. One part of the memory changes between each invocation. It's a little counter down there, and I'll skip forward a bit. So it's all just create, and it ends on create number 1 of 5, it goes out of gas. So by this time, you can kind of have an idea. So it's doing creates lots of times with a large memory segment totally filled with jump tests. It changes 1 little byte each time, so obviously bypassing any caching mechanisms. So by reproducing it and viewing at the trace in this fashion, we can do a very quick analysis of what happened. And we can benchmark it. Right now it's running at 300 milliseconds. And if I compare that to, so this is the EVM, get EVM with the patch applied after this attack. I can try it against the EVM without the patch for the jump test analysis. And as you can see, it took 9 seconds. So this tooling makes it possible for us to do quick analysis and then to check, does this patch work? And I can share it with the coworkers and they can try out various patches and see which one is the best. I can also run this in a web-like format and do all the same things and investigate other on-chain events. For example, sorry, which one did I take? That was the same. The parity wallet attack. And there we have the parity wallet attack reproduced. And you can run it locally, or you can check an annotated trace of what happened there in the parity wallet attack. And for example, yeah, so here's the fated infamous delegate call and the null attack if you wanna analyze that more in depth. So the EVM lab, which I showed you a part of, makes it possible to do some EVM assembly Pythonically and investigate these kinds of issues and yeah, dissect attacks on a really low level. We had 2 hard forks also, and in preparation of those, we ramped up the testing, introducing parameterized tests or generalized tests, which Dmitry talked about yesterday in the breakout room. And also put it all into Hive. Hive is Peter Szilagis' super cool framework for running nodes in a black box fashion, and just synthesize the environment, the genesis and the blocks and everything. And then you can compare the expected post state after a sequence of blocks. And this makes it possible to run, it runs about 24,000 test cases against Ethereum, Parity, Geth, and CPP. And it runs it 24/7, 365. It removes the dependency of the developers to perform tests as part of the test process. So now testing can be a totally separate process which doesn't really rely on the developers per se. The fallout, however, after the second hard fork is that we had a consensus issue, which was, yeah, definitely not what we wanted. Manually crafted tests are great, but there's no way to scale it due to the inherent complexity of the EVM. We can't just have enough people know that much about it to be able to scale it up. So we wanted more coverage for Byzantium and started looking into fuzzing. One way of doing that would be to generate test cases randomly, execute them on each EVM, and use this shared output format to compare the internal state after each operation. And just repeat it. And this can be done fairly quickly. You can do a couple of million tests per day if you use raw binaries, and you can use these 4 clients. The second track is based on libfuzzer, where we got in touch with Guido Rankin, who has done a lot of fuzzing and is a real expert on libfuzzer. So libfuzzer is the core of American Fuzzle. It's a fuzzer developed by Michal Zalewski. And it's a bit more sophisticated because it uses code paths and instrumented binaries to detect code paths for any given input and then mutating those inputs to maximize the code coverage. And since everything is instrumented and compiled into one big binary, it is an order of magnitude faster to perform these tests. So it can do about 100 million tests per day. And there was a spectacular and kind of unexpected success in this. We've had 7 or 8 consensus issues found. Most of them before the hard fork. One of them slightly after the hard fork. It has been fixed and patched and released. And the clients today, I would say, are more thoroughly tested than they have ever been in the history of Ethereum. And we are still running fuzzers 24/7, and it's been millions of tests done on the test path and billions of tests based on libfuzzer. Naturally, there can still be consensus issues or denial of service issues. And if that's really, really a concern of yours, then you should run multiple clients and try to detect mismatches. And you can use the debug method in Geth to find out if Geth has tagged one of Parity's canonical blocks as bad. And key takeaway here is that everyone here are targets for attacker. It's in bold because it's important. So be paranoid and be proactive and work on improving the security and your resilience and how you can handle attacks. That's about it for me. Thank you.